Okay, so we have just completed 3D in the last set of notes. Now we are going to look at the difference between strong acids and strong bases. So we have some notes to fill in. In the 22-23 school year, this set of notes is on the bottom of page 6. Otherwise, look for this heading in your notes to fill out the missing pieces. So it should be somewhere near page 6. Okay, strong acids and strong bases. Strong acids, acids that are completely ionized in water. That means they completely break down to H plus and OH minus concentrations. The position of the dissociation ionization equilibrium lies far to the right. So if you think about a balanced equation, we have the left side and the right side of the arrow. An acid's going to dissociate or ionize, far to the right. Okay, that would be right side of the arrow. The two things that's probably the most important, it yields a weak conjugate base. And we have talked about what conjugate base and conjugate acids are, and if we have not, we will do that shortly here. Next set of notes, for strong acid is the strength of an acid is inversely related to the strength of its conjugate base. So the strength of an acid is inversely that means 1 over, right? So inverse is the 1 over related to the strength of its conjugate base. I'll show you all of this here shortly. And the acid is much weaker than its water. Okay, so the acid is much weaker than, excuse me, I'm not saying this correctly. The acid is a much weaker base than water. So the conjugate of that, and I'll walk you through this here. Basically what it's saying is water wins if there's a competition between it and H plus. There are several that are listed. These are your strong acids. I will provide this list to you, and because if it was the real world, you would look them up or have them memorized, meaning if you were working in the industry, you'd probably have these already memorized. I can't promise that wouldn't be true if you were taking an IB test or a college course, but for this course, I will give you this list of strong acids and strong bases. So HCl, HBr, HI, HClO4, HNO3, and H2SO4 are all strong acids. Any other acid we would consider a weak acid. Now there are some arguments to be made or some way to prove something can be a strong or weak acid based on its Ka values. We will probably not get that deep into that, but that is something that you could use. Strong bases, they are completely ionized in dilute water solutions. Our strong bases all end in a hydroxide. So lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Again, I will give you a list of strong acids and strong bases. Okay, please jot this down on your index card. Strong acids, list those. It wouldn't hurt to go back and write down the strong bases just so you have them on your index card, although I will provide them to you. But for practice purposes, you might want to have them in a convenient space. So I'd write down both your strong acids and label them as such, and your strong bases and label them as such. And then this will make more sense when we go through these examples. Right now, just copy what you see in my blue writing. This stands for strong acid, weak conjugate base, and as the strong acid increases, the conjugate base will decrease. This is that relationship between the increasing strong acid makes a decreasing conjugate base, or an inversely related piece. All right, we'll get back to this here in a little while, and now we're going to go to example 4. Okay, example 4a, I'm going to go ahead and clear the screen and go through this with you. It says, what is the pH of a solution prepared by dissolving 2.38 grams of barium hydroxide per 10.8 liters? Well, I need to get pH. And what we know about pH right now is pH equals a negative log of H plus concentration. So we have to get to the point where we have H plus concentration from this. So let me walk you through how to do one of these problems. So as I had on the screen a moment ago, apologize, I cleared it here on accident. We're going to have pH. Let me get my pen working again. pH equals a negative log of H plus. We're trying to calculate pH here. So we got to use this formula. Before we can use the formula, we're going to write this, because we don't have any numbers that is moles over liters. We have grams and we have liters, but we don't have moles over liters. So we're going to take a moment to write this base. How do I know it's a base? It's an OH. as a dissociated or ionized. So to do that, we're going to take BaOH2 and we're going to break it down into the ions. The ions that make this up are Ba2+. How did I know it's a 2+? I looked at my ion sheet. And 2 hydroxide ions, which are a -1. So now you can see that this reaction is balanced because it shows, I'm just going to fix my horrible B here. We got there, okay. So what do we know? Well, we're going to have to figure out the concentration of this. Okay, so, and we're going to figure out the concentration of this piece, which is this. Then I'm going to show you how that's related. So we're going to take the fact that we know that concentration is moles over liters. Well, we have liters. So we have 10.87 liters. And I got to get moles. Well, remember that anytime I have the mass of something, I can figure out how many moles it is if I have a periodic table. We're going to calculate the periodic table number for barium hydroxide. Okay, sorry about that. This might have been a little fragmented. What I was trying to say that is we can calculate the concentration of something, big M, if we take the molarity equals moles over liters. We got the liters in the problem. And then I can get the moles of anything if I know its mass, and I can figure out its periodic table number. So that's the molar mass periodic table number. It's been a while, so I'm going to take a moment to pause here and show you how to do that on the next slide. So here I have copied a periodic table, and we know we need to do barium hydroxide. So we're going to take, I'm going to do it actually down here, 1 barium, two oxygens, pardon me, and 2 hydrogens. Remember, this 2 gets distributed through. So 137.33, that's barium's number, times 2 times 16.00, that's oxygen's number, and then 2 hydrogens times 101. So I took 1 barium, because in our formula we have 1 barium, so 1 times 137.33 is 137.33. 2 oxygens in the formula, so 16 times 2.00, and that is going to be 32.00. And then 2 hydrogens from the formula times 101 is 2.02. We're going to add those all up. So 137.33 plus 32 plus 2.02 gives me a molar mass of 171.35. So now back to the problem we were just working on. So this is going to be 171.35. Grams has to be here, so it cancels, grams to grams. So the opposite of periodic table number is always 1 mole of the same chemical. So that gives us our moles, because we're going to cancel grams to grams. So 2.38 divided by 171.35, and we would end up getting 1.3, and I'm going to round, 9 times 10 to the negative second moles. That has to go up here where we put moles in. So 1.39 times 10 to the negative second. I got that from the work below, and now we're going to divide the two to get moles over liters. 1.39 to the negative second, divide by 10.87, and I get my big M to be 1.28 times 10 to the negative third. To the negative third. Okay, let me write that up here. So that's going to go right here in this spot, because all of this work here gave us the value of 1.28 times 10 to the negative third. I'm going to make that a little bit cleaner. I'm going to try. There we go. Okay. So all of this work here I'm going to erase in just a second, but you do want to show that work. You will get points for it, showing me how you got the molar mass, and then how you got the molarity, moles over liters. So let me take a moment to erase that, because I need to show you some more pieces. So you might, when you do a problem on your own, do this piece a little bit further down than I did on here to help you with that, with spacing. So all that work got us to the 1.28 with rounding times 10 to the negative third. Now, in this dissociated or ionized reaction, this is a 1 to 1 to 2 ratio. So therefore, we would know this would also be, well, let me get my pen instead of my eraser here, 1.28 times 10 to the negative third, because it's 1 to 1, but this is twice as much. So then I got to take 1.28 times 10 to the negative third times 2, because it's a 1 to 2 ratio. So 1.28 to the 3 negative times 2 would make this be 2.56 times 10 to the negative third. Okay, so what we now need to do is go through the next piece. So let's go through that. All right, so all of this work that we have done so far has nothing to do, well, that's not really true. What I should say is it's not answering our question yet, is what I meant to say. But we do have a way to get to the answer now, because now we have, right here, I'm going to circle it in green, now we have a value for OH minus. But it took us a long way to get there, and that's just sort of the complexity of this kind of problem. So now I can say, I want to get pH, but I have currently, from all of this work that you see here, the OH concentration value from this is 2.56 times 10 to the negative third big M. I want to figure out pH. So I'm going to choose, and there's several ways, just like before, that you can attack this, to figure out pOH by taking the negative log of my OH minus. Okay, and again, there are several approaches. This is not the only way. Answers could slightly vary based on all of the rounding we're doing throughout. So I'm going to punch in. We're going to take negative log of 2.56 times 10 to the negative third. So 2.56 EE negative 3. I'm going to hit the negative or the log of that and take the negative or negative log depending on your calculator. You're going to get 2.59. So what I did on my calculator is I took negative log 2.56 times 10 to the negative third. Remember, for times 10, we're hitting the EE button. And you get 2.59. This is a 9 for pOH. So now I can, I didn't even end up using this. I'm going to show you how to use this method in a moment. But I can do pH is equal to, well, better said, let's not do it that way because I might confuse you. Let's go with the basic formula. 14.00 is pH plus pOH. We just figured out pOH of 2.59. So now we're going to take 14.00 minus 2.59, and I get my pH, if I may do it over here for purposes of not needing to move my screen, of 11.41. So we have solved one way that we can solve this problem. Let me show you a second. And there's more than two, but I'm going to just show you two today. Okay, when I originally started this problem, I wrote this formula here as an option. Then I showed you a different way. Sorry about the confusion there. Let me show you the way to use this formula. Either one would be fine, and we should get the same answer or nearly the same answer. To use this formula to get pH, I have to have H plus concentration. All of this work would still need to be done the same way we did it. So all of this would still need to be done. And then we can use that piece, finding the OH concentration, to get H plus concentration, then plug it in. I'm going to leave some space here, and then I'm going to say that I know that 1.0 times 10 to the negative 14th equals H plus, just another formula we've been using, times OH minus. So 1.0 times 10 to the negative 4th equals H plus is what we're solving for, because this formula did not give us H plus because we were provided a base. So instead of doing square brackets, let me make that a parentheses. We had figured previously, based on getting our molarity, our moles over liters, 2.56 times 10 to the negative third. Okay. And we're going to take 1.0 in our calculator. And oops, I didn't have my 14 there. I wrote it, but the pen didn't pick it up. 1.0 to the 14th negative, divided by 2.56 to the third, 3 negative. And I'm going to get my H plus concentration to be 3.91 times 10 to the negative 12th. And then I can go plug that in here. Negative log of 3.91 times 10 to the negative 12th equals so I'm going to have my calculator negative log, and I get, with rounding, 11.41. So same answer I had got doing it the other way. So either way would be sufficient. It doesn't really matter which way you do it, just as long as you're showing me how you're getting to your answers by giving me generic formulas and plugging in numbers where appropriate.